assignment one was about our public perception, public engagement for Sydney water use, potable water purpose. So you have already experienced how to engage with the public. Now we started an assignment to membrane bioreactor energy consumption, space requirement, and footprint. So now it's last our task, design of a seawater desalination plant. So already we had a little bit of discussion seawater desalination at the beginning of this class. So we mentioned about what's the Sydney water history of wastewater use and desalination. So we have utilized this plan to secure our sustainable water resources. So now it's time to look at more details and then dive to the design as well. So how to design seawater desalination plant. So we have to understand what's the principle of this technology, and then how we can separate desalinated water between salt and water. And that's we want to finalize this class. So before we start, how many people already look at our reading materials or videos? No worry. This is all right. So we have to know today. Yeah. So we can learn from their lectures. Also, how many people know about what's the last assignment in this block 3? So we need to design seawater desalination plant. So this is the 35% of your score. And we need to look at how to make a process of the seawater desalination. So based on the scenario, already you are very familiar with scenario because of assignment 1 and 2. Now it's assignment 3. So first question is about how to make your seawater desalination process for Sydney seawater. So you need to decide what kind of process we have to utilize. And second question is, what's the design of reverse osmosis to desalinate your seawater? So you have to understand what's the design factors, what's the volume, and how we can make all the detailed processes, membrane, and also brine management. So when you have brine, so how we can maintain this one without any environmental issues. So that's the also third question. And first question is, what's the brine management resource recovery? So seawater contains more than 100 elements inside. So how we can extract useful and valuable material for a circular economy. So that's we have to design how we can consider what kind of material would be the value for seawater brine resource recovery. and you can finalize your assignment 3. So today, we will go through together how to design seawater desalination plant with resource recovery, brine management. And tomorrow, 11 o'clock, so you can come to the computer room and we can try your software, wave software, to better design your reverse osmosis technology. And how many people installed the wave software here? Okay, 1, 2. So you can register your account and then you can log in, download, or I emailed you yesterday how to just to directly download from our
Yeah, but I downloaded it, but I can't manage to open it. Like when I open it, it doesn't work.
Doesn't work. Did you follow the installation?
You
download my files or
you don't find
my file?
like
You download and install and then you try to open it as well.
when I do that, and then
Yes.
and that's all. Yeah.
Okay. Can you download from the internet? So you can access again and you can try it because this is free. Sometimes they have a little bit of error. But tomorrow we have computer room. We can try.
And tomorrow is from 11 to
11 to 2. Because from 2 to 5, so you can continue your assignment in the computer room lab. Other type of software information you can access at any time for your computer room for your assignment 3, especially Apple. You can install the software for Apple computer, so it has to be Windows operating system. So if you don't have a Windows OS, you can come to the computer room and then do your. So tomorrow lecture will happen from 11 to 2, then from 2 to 5. So you are free to stay, or you can go back home, or so you can continue to your assignment. So that's the reason why you can have some selection of your choice from 2 to 5. So please come 11. So if you understand this class today, tomorrow, so your assignment will be much easier. Otherwise, it will be a little bit difficult to follow up because it's a design assignment. So there is no clear answer for your own assignment 3. So everybody should be different from your own design. So you can have a better understanding of this class, and then you can try yourself. And you can also put some of the computer software design and capturing your screen and then put into your assignment. Also, you can summarize the detailed design parameters inside the report. So you have flexibility. Also, we have a consultation timing. So just before 1 week, we closed our assignments, so we can organize the consultation time as usual. So you can come and then have a discussion. It looks like everybody is very smart. I saw first consultation for assignment 1 was only 4 people. The second assignment was 5 people. So it looks like everybody is very confident to do your homeworks. So it's a very good sign. Yeah, if you're already very much clear about what to do for your assignment 3, yeah, you don't have to come. But if you have any question, specific, any problems, you can come to the consultation timing. Otherwise, you can just send the email. We can organize our maybe in-person or online meeting, so we can have a discussion together. Any questions? Everybody is very familiar with this subject, right? So it's good to know that. So what we will learn from this lectures, so what we have to study to design a wastewater desalination plant. So we need to know what's the inside of seawater first, and then how this seawater can be separated with the water and salt. What kind of technology would be useful to desalinate the water? And we have to also understand a little bit engineering terminologies. The key terms used to describe the membrane processes. So you can have us at the same page to discuss what's the module, what's the element, what's the diagnostic, what's the CIP. There are specific terminology we can utilize for your assignment, and then you can mention about in your design. Also, water quality. Seawater water quality is different from wastewater, drinking water, even groundwater, rainwater. So every water has a different. So how we can identify the quality of seawater, and this will impact overall our processes and seawater desalination plant design. So you have to understand what water quality parameters will give a different selection of our technologies or processes. So we have to make sure that all the water quality parameters. And reverse osmosis. So what's the reverse osmosis? So you remember the first day I showed you reverse osmosis membrane. Like this, like a paper. So this reverse osmosis membrane can separate your salt and water molecule. Yeah. How? Pressure. So driving force is the pressure. So how much pressure do we have to apply? A lot. That's correct. What's your blood pressure? What's our blood pressure? Okay. So we have pressure in our blood, right? It's like a driving force. And then blood pressure continuously flowing our body from our brain to the feet, right? And blood carries nutrients, oxygen, and some of the useful cell. Yeah. So how did it happen? Because our body is like a membrane. like this. The nutrient goes to our body, oxygen was transferred to our body, make the body healthy, right? So this is similar. This is a polymeric artificial membrane. Your body is bio membrane, even like a cell, right? So it's a similar principle we have. So you have seawater will pass through this membrane. You have salt, you have water. The water molecule will pass through this membrane, and salt will remain in this barrier. That's how it works. Okay. So what's the water? What's the size of the water molecule? What's the size of one single molecule, H2O? What's the size of water molecule?
275 nanometers.
0.05 nanometer. 0.05. From ChatGPT or from DeepSeek? Or from where?
275 nanometers.
What the molecule is the diameter of okay, 0.275, right? 0.275. So around the 0.3 nanometer. So 0.3 nanometer, one molecule is 0.3 nanometer, right? So what the molecule is, one single molecule is 0.3 nanometer. So 0.3 nanometers will pass through this membrane. How about sodium, chloride, salt? So there are 100 salt in seawater, right? So what's the molecule? Yes, sodium chloride is the highest concentration of in seawater. The sodium, what's the molecular size of sodium? So we are looking at the molecular level of how we separate.
0.190.
0.190. So let's say 0.2 nanometer, right? So as I mentioned, water molecule is 0.3 nanometer, right? So water molecule pass through 0.3 nanometer. And you mentioned about sodium is 0.2 nanometer. So they have to also pass through, right? Yeah. So what happens? The water molecule 0.3. The sodium is 0.2 nanometer. It's much smaller than water molecule. How we can separate sodium and water. So that's the water chemistry. So what you are seeing is very much error level of size. What happened? So how about, let's think about table salt. So you every day you take table salt because salt is very tasty. You know, barbecue without salt, the taste is not really that good. So salt, sodium chloride. So you are taking this salt. So if you see the table salt, what's the color of salt? White. The sodium chloride is white, right? Then it looks like the powder pie, right? What's the size of your sodium chloride table salt? That's the size in a table salt. Okay. 0.1 millimeter or 1,000 nanometer, right? So you can see the naked eye table salt. Yeah. So when you have a table salt, it's white color powder. And then when you put into the water, okay, you have a salt. Okay, let's just put into water. Yeah. So this table salt dissolved in your water. So what happened? Can you see your white color? Can you guess what happened inside your table? So it was white color and then like granule size, maybe 1 millimeter. Yeah. But when you put it into the water, what's happening? So you can think about, okay, your table salt, put it into the water and completely disappear inside water, right? Why? Dissolve. That's correct. How? Break down in water. Okay. That's why it's you have to understand what is going on inside. So you can easily understand why this reverse osmosis membrane can separate what molecule and salt. So let me add a little bit of water chemistry. So we have a white color of the table salt. It's granule. White color. It looks like if you look at microscope, it's cubic size. Right? They are all aggregate each other. So it looks like bigger size, bigger size. So you can see like a powder, white color, right? But if you look at the one structure, crystal, so it looks like a cubic kind of the structure because sodium chloride, sodium chloride, sodium chloride, sodium chloride, sodium chloride. The sodium has the atomic number is 11, right? Then chloride is 17. So 11 has a 1 proton. Yeah. And Cl minus, you have a minus. They combine sodium plus and chloride minus. So they are attached to each other. So this one is keep repeating. So sodium chloride, sodium chloride, sodium chloride, and continuously, finally they create the cubic structure of your crystal. When you don't have water, right? So you can see cubic structure. Now, this cubic structure we put into the water, yeah. And what happening? So water molecule has H2O. The H. O. So let's say this is the O, oxygen, and then this is hydrogen, H2H. The H2O, H is the plus charge, oxygen is the minus charge. So water is a very good solvent because it has two charges, one plus and minus. For example, sodium is only one charge, plus. Chloride, only one charge, minus, right? Sodium chloride. But water molecule has two charges. The plus minus together. H has plus, oxygen has minus. So one molecule has two charges at the same time. So I want to put your table salt in your water. And what happens is sodium chloride start dissolve in the water. And they see the single ion, sodium plus, chloride minus. So sodium chloride, now it's a lot of water molecules around in your water, right? So water molecule has the plus minus at the same time. So you can see the sodium here. So sodium plus charge combined with the minus oxygen. So sodium and H2O minus oxygen. So they try to cover your sodium atom. So you mentioned about 0.2 nanometer of sodium at the molecular level without any hydrated condition. So when you have a inside water, the sodium never ever stay alone because water molecule easy to combine with the plus charge minus oxygen. So water molecule is surrounding the sodium molecule atom. So real size of sodium, even though it's a 0.2 nanometer, right? And if you look at the hydrated side, it's around 0.6. So we just say hydrate with the molecule of sodium. The hydrated sodium size is 0.6 nanometer. So what the molecule is 0.3 nanometer, yeah. Sodium is 0.2 nanometer, but inside the water hydrated together 0.6 nanometer. So you have 0.6 nanometer of sodium water molecule, and you can separate your water and sodium. Also, look at the chloride. So this time the chloride is minus charge, right? So what happens is that water molecule H, 2H will attach with your chloride ion. The chloride itself, the atom size is around 0.4 nanometer. So they combine with the H2O, right? So hydrate together, and then you have a hydrated chloride size. So this is much bigger than sodium hydrate size. So that's exactly we like to separate water molecule, sodium, chloride, even there are many different ions can be separated from the seawater salt and water molecule. So that's how it works. But if you dry again, okay, you have a seawater, you just dry and then water molecule is evaporating. Yeah. So what happens is again, sodium chloride plus minus is combined, sodium chloride, sodium chloride, sodium chloride, and then you create the cubic structure, crystal. So you can see the white color. And then this is the without any water. So that's the how we can utilize the separation of salt and water molecule. So this is the polymer membrane separation using this reverse osmosis membrane. So let's think of our body also, say, membrane, right? Our body, our cell, yeah, and our inside. So where is the outer membrane in our body? Stomach. 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 Possibly. What? Skin? Skin. 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 There's also. Yeah, right. Skin. So it looks like very soft and very much close. So when you have a heartache, And then you just sign on that. So your sweat is coming out from your skin. From face, then from your eye. So it just, you have to sweat because you are too hot, so try to control your body temperature. So that you have to release your water molecule to your, from your body, and you can lower your body temperature. So when you are in the bathroom, when you take a shower, for just 5 minutes, 10 minutes, so your skin is not a problem. So when you stay in your bath, for 1 hour, 2 hours, so your skin is swollen, right? Because of your water molecule penetrate your skin. So this is the membrane. So your water molecule can go inside your skin, then keep accumulating. So your skin structure is very much swollen because of water molecule. Also, your kidney. Yep. What's the function of kidney? Yeah, filter outside our body, which could be not necessary for our body. So blood is keep flowing. So blood has around 1 gram per liter of salt inside. So what happens is that after you circulate all the nutrient oxygen, so you have a very Dutch material which cannot be observed from our body. So this will pass through our kidney, and at the time, the kidney has a membrane like the reverse osmosis, and you have a high concentration of salt. So your bloodstream has a low concentration. So when you pass through your bloodstream into your kidney, the kidney is membrane. But because of osmotic, like concentration gradient, so your water molecule and your nutrient and your harmful compound, which cannot be observed from our body, pass through your urine. So if you look at the urine, your urine, so it's filtered by our kidney membrane due to concentration difference. The kidney extracting your nutrient, urea, and some of the harmful compound. So when you urinate, what is inside of your urine? Urea. Urea, yes. Urea is the highest concentration. Because why? Because urea is the easiest way to pass through your membrane. Because urea has no charge. So there is no charge. If you have no charge, there is no interference of the cross minus or electrical charge. So urea is the best way to discharge from our body. So urea, what is urea? What's the urea?
All the bad stuff inside our body.
What's the molecule of yeah? What's the molecule of urea? NH2. NH2. Very close. C2H NH2. So carbon and nitrogen. So which means we uptake a lot of food. The food contains nutrients, nitrogen, phosphorus, potassium, calcium, magnesium, vitamin. Sometimes some people take Panadol. Panadol has a specific chemical compound. So Panadol or drugs or nicotine, caffeine, any of molecules. If it cannot be absorbed, it will be discharged. Otherwise, we keep accumulating our harmful compound and then will be that's a problem, right? So our body keep discharging, which is not necessary for us. So that's exactly kidney always trying to discharge nutrient, harmful compound. So this membrane is continuously work. So your urine, there are a lot of nutrients. Now, like phosphorus, potassium, calcium, magnesium. Even some people drink alcohol, because alcohol is discharged from the urine. So any kind of compound can be separated from it. So that's exactly our natural membrane is in our body system. And this is coming to our technology. Reverse osmosis inspired by our human body, human cell, human membrane. Then we can artificially utilize pressurize rather than osmotic pressure. Concentration different. We just use pressurizing, like apply from artificial pressure to separate water molecule, urea, nutrients, even salt, any kind of compound. So that's we have to learn about reverse osmosis, forward osmosis, natural osmosis. This is like a driving force, how we can utilize for reverse osmosis for desalination plant. So that's we want to look at a little bit more details and how we can design for your assignment. I want to design seawater desalination plant. So when you design your kidney in your body, every day you produce around 1.5 liters of urine. So we design our kidney for 1.5 liters per day of membrane size, right? Of course, depending on how much water you drink, you will discharge more. But in general, 1.5 liters of urine we produce every day, right? So your kidney is designed for 1.5 liters. Now, we want to design seeded desalination plant every day, 250 million liters a day. And how many modules we need for reverse osmosis? Then how this membrane can be attached at the surface area, and how many buses? We just say this is the module and element. So how many modules we need with the certain surface area of membrane, and what pressure? Okay, we pressurize 10 bar, 20 bar, 60 bar, 100 bar. So what pressure we can tolerate this module? What pressure we can produce how much in desalinated water? That's exactly we have to look at the design of reverse osmosis. So that's how we have to think about it. So it's like 250 million liters per day. It's quite a lot. So you cannot utilize your hand calculation manually. So we need a little bit of software. Yesterday we shared together, and then we can download. who installed this one without any problem? Have you ever tried with this? Like some people have issues to open the software. Did you download new version?
Tried like I didn't manage.
Okay, so you try with the internet and see. Otherwise, we can do tomorrow. Or it's better to you can try yourself today or after class today, and a little bit of fun, like a computer game. You like it? Yeah. But it's similar. You click and you can see very interesting data and video. This is very good reflection of the assignment. So we need to look at detailed design. We're using the software because manual calculation design for this kind of size, we have a lot of mistakes, errors. So better to use but we have to understand what's the principle behind this design. So that's how we have to look at carefully today. Was case study citizen desalination plan. So your assignment is designing the citizen desalination plan. So that's exactly you have to put into your assignment, design process, also detail. And good morning. And we will learn tomorrow what the application value and the wave software in a computer rooms. So we can come around 11 a.m. and we can try this software. Also, integration, how to integrate our overall process. So that's all about today and tomorrow. Any questions so far? No questions. Very clear, and let's go one by one. Yeah.
Can you explain a little about like reverse osmosis, natural osmosis?
Reverse osmosis and natural osmosis.
What's the major?
Yeah, reverse osmosis. Like that's exactly we have to learn. One of our lectures. So we have a special content, osmosis. So you have to understand first the osmosis. What's the osmosis? What's the reverse osmosis? What's the opposite of reverse means forward? What's the forward osmosis? So osmosis. That's exactly we will cover maybe in the afternoon or
What is happening in our kidney? Is it normal forward osmosis or reverse?
because our body has low pressure, right? So we rely on the concentration gradient, so which means osmotic pressure. We just say not the pressure, apply the pressure, but natural concentration pressure. We just say osmotic pressure. So you have a membrane here. You have a very high concentration, low concentration. So your high concentration will suck your water molecule through your membrane. So just say this is the osmosis. So concentration difference will make your osmotic pressure, not the artificial pressure. So that's how our body, our kidney, our skin happen to us, natural osmosis. But reverse osmosis is opposite. So we have to, osmotic pressure is concentration different. But seawater has very high concentration. We want to separate the water molecule salt. So you need to pressurize the reverse osmosis, and then it goes to the reverse way, right? So that's we will understand theory, because osmosis was discovered 1900. The Van Gogh. He got a Nobel Prize of the chemistry. So if you got the Nobel Prize by discovering, so by discovering this osmosis, so he calculates how we can convert to the pressure, how we can convert to a parameters. So you got the Nobel Prize. That's exactly you have potential to get Nobel Prize. When you ask him, what's the osmosis? That's exactly Van Gogh. 120 years ago, we questioned where he discovered, oh, this is osmosis. We got the Nobel Prize. We have to try the Nobel Prize. Yeah. I think you have a good question because that's how it works, you know. So we will make a detail and
This osmotic difference, what we are trying, if it's just extracting out the water molecules, what about the dissolved? The concentration is still there. Although it's low concentration, but it has something.
yes,
So if water molecule is getting,
yes, yeah.
so we will be left with some residue.
But the concentration was higher. So in a certain state, we have to push out, or otherwise it continuously creates osmotic equilibrium. So there is no more osmotic pressure because concentration. Okay, right. So let's see the general information, seawater desalination, the SWRO. So you can see in Australia, we have 6 major plants of seawater desalination. So seawater desalination becoming more important because everywhere now it's climate change, weather condition, drought, especially Middle East country, Africa, even Australia, Western Australia, South Australia, Sydney, yes. So we need a desalination plant. At the same time, our population grows. And we need more urbanized world. So like Sydney, if we don't have enough population, our water of that Blue Mountain water reservoir wasn't enough. So we have increased very significantly last 30 years. That's the reason why, yeah, it's not only about we are in problem of drought due to climate change, but also increasing the number of people. And we have to figure out water resources. And desalination market is keep increasing. So you can see last 10 years, the BWRO, SWRO, seawater desalination increased very significantly. So you can see how much money. This is only for capital cost. So you make for one desalination plant. Consider desalination plant, we spend $2.1 billion to make that plant for that KFC.
What's the capacity?
That is in your scenario. 250 billion, yes. So we already spent a lot of money, and now we have to expand our plan. And look at the overall market of the seawater desalination plant using membrane. It's almost 6,000 billion. So which means 6 billion for only capital cost. And operation cost, because you need a pressure, you need a membrane, you need cleaning, you need also maintaining. It's double. So which means operating cost per annual, so it is around $12 billion. It's every year. I'm not talking about the whole life cycle of a plant. Every year in the world, we spend around $20 billion because of seawater desalination plant. So it's like a very big market, and everybody want to have an innovative idea to develop this technology. And this is the number. The desalination, $6,000 for capex. OPEX is around double size. And then we have a contracted and operating capacity. Water use at the same time increased. Already you have experienced in your wastewater use the last assignment to water use. The water use also keep increasing because seawater desalination is expensive than water use. So people like water use is much cheaper, not much cheaper, little bit cheaper. So better to go for wastewater use. If you are in that area, if you have enough wastewater, so you can utilize this kind of wastewater reuse. And seawater desalination, it's depending on your coastal line, and then it's expensive. But people like to drink the seawater than wastewater recycled water. So wastewater recycled water, people are a little bit concerned about this is the year for the first water. I don't like this guy. And then he has the toilet fresh water, recycled water, and it purified. I don't want to drink. Some people have this kind of public perception. Or seawater, or we are swimming inside seawater and salty, and you like more, regulated from our perception. So people into seawater desalination looks like that much more clean.
For desalination, why don't we just opt for distillation process?
Over
Distillation, right?
distillation, okay. Distillation will occupy. So you are already little bit ahead from my slide. So we talk about distillation. So first, we like to talk about reverse osmosis because distillation is much slower. That's the reason why.
Boiling water is increased.
That you have to do. So people like seawater desalination is very comfortable to drink. But wastewater recycle still, some people do not like it to drink. So how we can, even though technically we have a very high quality of water we can produce from our reverse osmosis, but people have a perception, this source is from wastewater, this source is from seawater, this source from rainwater. So we need to also make sure it's not about technical issue, it's about our public perception engagement, so that our first assignment already you have successfully completed this public perception. Now it's water reuse. It's also one of consideration we are looking at, and seawater desalination. This is a history of our seawater desalination. First day, I remember I already explained about what's the history of seawater desalination, right? So can you please explain what did I mention about seawater desalination plant in the first day of our class? You were not there, right? Okay. No one was there. Sir? What did you say? Anybody? Okay, this is the history of seawater desalination plant. We need to design. So, seawater desalination plant Now, how much we are producing?
This is normal,
None. So that's why, okay, where is your water, how about the source from? Where do you? On street. On street.
I think. Not there.
Okay, what about the dam? You're right, but your water is not covered with desalinated water. The desalinated water is in the city. Based on city, because city has more water consumption. Water needed need cover city area. So if you live in Sydney, so you are combined with desalinated water, yeah. How many percent? So anybody tasted our city campus drinking water? What's the taste of
Just like normal.
normal water? It's true, no, not many people can identify. You have 100,000 bottled water. Okay, we have bottled water here, yeah. So why do you like this brand?
I just refilled it. It's on the top.
From the tap. Okay, it doesn't matter. So you don't mind the coolidge.
Well, I wanted like once and then I just kept refilling it.
The coolidge water, yeah, also. And what's the most selling brand in Australia?
No.
Have you ever heard? How much cheaper? $5 bucks.
Pay that.
So, Mountain Bentley is from Victoria, right? The area is the mountain Bentley. It's not brand of, in fact, the area they are collecting this water is the mountain Bentley, right? So why this is expensive? Why this is a little bit cheaper, or even cost? They have some cost bottled water, right? It's much cheaper than Evian or any other brand. So, what's the inside? What's the inside of mountain Bentley? Mountain water. So this is the spring water from groundwater. In this area is relatively clean. So they just collecting this groundwater, clean it, and they are selling this water. How about other water sources? They are basically similar. Spring water, yeah. So there is nothing much different. Even tap water. When you drink tap water, the major difference is chlorinated or not chlorinated. So your bottled water is not chlorinated, right? But your tap water is chlorinated. So you have chlorine inside. The other hand, in your bottled water, there are a lot of microplastics. Because this is a polyethylene. Yeah, it's like a polymer. And looks like you cannot see it inside. But when you have sunlight and UV will attack your polymer, and they slowly release the polymer. Also, when you breathing this water, or you put it into the hot water basin, boil the water, and then this water is plastic. Even though you cannot see from your naked eyes, this structure inside even this polymer continues to release your microplastics, small molecular polymer is released. Even though it stays for a long time, 1 year, 2 years, 3 years, this structure is continuously breaking down. So when you drink tap water, so you have a chlorinated water, which may create the carcinogenic compound, chlorinated organics. But when you drink the bottled water, you would have more microplastics. So which one do you want to drink? Tap water or bottled water? Bottled water is better. Yeah.
Till now, we don't know the effects of microplastic in our body.
So let's prove it. The microplastic flowing through your body, and then you have a small, your blood cell in your brain. Yes, everywhere. Yes, everywhere. So they cannot dissolve. So you may have a clogging problem or a stroke problem. Of course, depending on how much microplastic you okay, then affect your body. So, however, compared to bottled water, it's true, you have more exposed to microplastic. But so far, people believe, okay, I'd like to have a more microplastic, easy to carry, but easy to avoid any contamination from tap water. Even tap water, we don't know. This is natural source. So you don't know what is the natural source coming through Oregon Dam, Blue Mountain. So how it's contaminating, how this is exposed to PFAS, how this has, another health concern. So it's up to you. No matter what you drink, there are always uncertainties. But fortunately, you don't drink much. Every day, 2 liters, 3 liters, 5 liters. Yeah. So it doesn't really affect our health. Because otherwise, you have a very high concentration of this kind of contaminant. So, seawater desalination, this area we have at this moment less than 5%, because we have a lot of water. Today it was raining. Last week was raining. Now it's relatively good rainfall in Sydney. So in this case, we don't need a desalination plant because it's very expensive to separate salt. So they want to have a minimum operation. But when they have a little bit low level of rainfall, drought, and then they start increasing. Maximum, we can cover 15% of seawater desalination. So what you are drinking in the city campus, in the city area, it's a very small amount of desalinated water is combined with the water of that. So mostly this water source is from water of the dam. So that's how we are now going through Sydney desalination plant. But
do they have any particular timing, like, okay, from this time to this hour, we will provide you seawater or desalinated water, or like rest of 20 hours, we give you normal water, or they just mix it in?
they just mix every time. So
there is a-
where is the, okay, I will show you video how you are getting your water source in this area. So you will get all the details soon. So this is the 6th desalination plant. which are very, very big scale of desalination plant. But there are more than 1,000 desalination plant in Australia, small scale, like Central Park. We have a wastewater reuse. It's like a desalination, reverse osmosis, 1,000 cubic meter per day produced every day. Also, we have a wastewater from industry, even drinking water, even recycling water, or industrial recycling water purpose. We have more than 1,000 desalination plants. So seawater desalination plant is the largest scale and the most difficult to design, most difficult to handle. So we just target seawater desalination rather than small desalination plants. So just look at the 6 desalination plants in Australia, how to design better. So let's see, Gold Coast. The Gold Coast reverse osmosis desalination plant is shown here. So you can see every desalination plant consists of reverse osmosis because it's cost effective than distillation. So we select this reverse osmosis. So this is the configuration: drum screen, dual media filtration, cartridge filter, second pass SW, water reverse osmosis, CO2 remineralization. So your first assignment question is about design your processes. So this is the example of Gold Coast desalination plant. They have this kind of water processes. And seawater not converted to drinking water is returned to the ocean through underground pipeline. A 200-meter long diffuser system releases the water in an area about the size of a football field. After they produce the water, and brine is returned to the ocean, and they have a diffuser to release back to the ocean. So this is like a dilution of the brine after we produce the water molecule. So Gold Coast produced 130 million liters per day. How about Victoria? Victoria, Melbourne. Anybody live in Melbourne here? Nobody, right? You live in Melbourne?
It's going to Melbourne.
Yeah, maybe. So Melbourne. Okay, Sydney has the Warragamba Dam, Blue Mountain, everything. How about Melbourne? Which water sources is in better situation compared to Melbourne? Sydney? Melbourne has a very strong water resource. We have a very good rainfall compared to Sydney, because they are cold and they have better water condition. So they have a very good reservoir system in Melbourne, but they never have expected to make the desalination plant. But during the millennium drought 20 years ago, everybody worry about water resource. Then Sydney started with the desalination plant, even Gold Coast, Adelaide, in Perth. So even though the Melbourne was not in a serious condition, every major city, they built one desalination. Why not we also want to secure our resources. Then they built it, a very big site, 440 million per day. Never operate. They have a plan. They are maintaining, but they have after millennium drought, enough rainfall, and they never ever operate. So this is like a future insurance to make sure that just in case in the future more population, maybe some more drought, it could be possible, but they never ever use this kind of seawater desalination plant. So this is the Victoria plant, and this is Adelaide. So if you compare other plant, so if you see Gold Coast is the dual media filtration and reverse osmosis. The Victoria desalination plant is dual media filtration and seawater reverse osmosis. And Adelaide is this ultrafiltration. The Victoria, Adelaide, Victoria, Gold Coast was the dual media filtration. But Adelaide is ultrafiltration as a treatment and reverse osmosis. So what's the difference? So you need to select your process for your assignment, which you like to do, ultrafiltration or dual media filtration. There are pros and cons, depending on your water quality, depending on your design, depending on your design parameters. You can decide from your assignment. So you can have, if you like the ultrafiltration, you can design through ultrafiltration reverse osmosis. If you like dual media filter, like even pulse, dual media filtration and seawater reverse osmosis. How about the southern-south desalination? The pulse, Western Australia, especially very dry area. So they have two major desalination plants. One is the dual media filter, and the other one is ultrafiltration. So this is ultrafiltration. Reverse osmosis is very small pore size, but ultrafiltration relatively large pore size as a treatment for reverse osmosis. So southern seawater desalination plant Impulse and Adelaide utilize ultrafiltration as a treatment. Rest of that are utilizing the dual media filtration. Like a sand filtration, so you have a sand filter, natural media filter, which is very conventional. So you have to decide your design, whether you want to do intake, pretreatment, ultrafiltration, dual media filtration, or sand filtration. That's your first task.
In dual media filtration, one is sand, another is.
Dual media filtration, multimedia filtration, people using the sand, anthracite, granular. So depending on what they like to do, so they have a different media, like a natural sand or different, even sand has a different size, different structure, different sources. Also, some people utilizing the activate carbon filters. So there are different way of design, but in your assignment, you don't have to go for that much detail of which kind of media filter you have. Just the design media filter is media filter, right? or ultrafiltration. So you can utilize ultrafiltration as a treatment for reverse osmosis process. So depending on your confidence or your knowledge, and you can decide in your assignment ultrafiltration as a treatment or media filter. That's the major difference of your assignment 3. So you design this way, your design parameter will change. You go for ultrafiltration, you have to go for different design process. So it's up to you. You can select whatever you like, and then you can have. How about seasoning? So we are here. So let's look at the more carefully seasoning. At this moment, we don't operate fully. It is the desalination plant because we have enough water sources. So it was designed 250 million liters per day. The site covers 45 hectares, located on the coast of Cornell, near airport, and 25 kilometers from Sydney's central business district. And open, the process is intake, diffuser outflow, drum screens, fuel media gravity, micro cartridge filtration, two-pass reverse osmosis membrane, and lime post-treatment, chloride, CO2 remineralization. So that's the process. To produce your seawater to drinking water, so how many processes you have to go through? So how many you have to design parameters? So you have to understand everything, how to make your perfect design. And specifically design outlet modules ensure that water returns to normal seawater salinity and temperature within 50 to 75 meters of the outlet. Approximately 58% of intake water is returned to ocean. So which means you have a 42% recovery rate. So you collect 42% of drinking water and 58% discharge back to ocean. So that's what we are drinking. At this moment, they can operate 250 million liters per day. Only 5% they are operating now. Then mixed with your dam water, and you are drinking here every day in this building in the city area. So this is the desalination plant location. So we have Botany Bay, airport, also we have UTS, and the water desalination plant located in this area. So they produce and then supply to city area. So let's have one video. What's the seawater desalination plant looks like. This is the media filter, sand filter system, or dual media. This is the reverse osmosis. So you have to design this one in detail. So 1.5 billion people benefit from the desalination in this area. You can see the main city. If you live in this area, you have desalinated water combined with the dam water. The taste it's not different. Even we can identify this water much. Unless otherwise you have a very strong chlorinated water or some of the high salt, like you have seawater. When you swim, so you taste the seawater, yeah. This is 3.5% of salt concentration. Is it very salt? Or how do you feel like when you have a seawater tasting is very salty, right? This seawater is salty, or let's say Japanese ramen or seafood lobster. Which one is salty? So seawater, drinking water, even Japanese ramen, seafood lobster. The salt concentration is seawater is 3.5%. Yeah. And then like a Japanese ramen, salt concentration is around 10 grams per liter, 1%. The difference is that Japanese ramen possibly put MSGs, like organic, yep, some additives to make a little bit taste better. So you feel like a different way of salt. Yep. So when you consider you have a 3.5% seawater, very salty, and then you have a different soup, yeah. Then with less than 1 gram per liter, 1%, 10 grams per liter. It's a different way of salt concentration. So we have to look at 3.5%. We have to remove from seawater and taste depending on what's the salt. And we have to look at more carefully in this desalination plant design. So you can see the process. So this is Sydney desalination plant, very much very general and typical way of desalination. The one desalination plant, the reverse osmosis, consists of this kind of very simple and typical, more than 60%, 70%. They utilize the seawater coming through. So seawater is salty, 3.5%. How about pH? How about seawater pH? 7.5, 8. Huh? The seawater is higher than drinking water. So you are drinking 7, pH is 7. For seawater is 8.1 or 2. So 8.1, seawater is a high pH. So what happens if you have a high pH? So when you drink the seawater, pH 8, what's the taste about? Only you realize the salty, right? So you cannot identify pH 8 and 7, how it is different, right? How about Coca-Cola? What's the pH of Coca-Cola? Acidic. What's the pH? What's the pH of Coca-Cola? Coke. Never thought about because 2.6. Wow. Coca-Cola. 2.6. Yeah. Seawater is 8.1. Coca-Cola is 2.6. How about lemonade? Sparkling water or lemonade? Acidic. Okay. You like lemonade or lime contained some sparkling water? Every sparkling water has a very low pH. pH 2 or 3. And you make feeling like a more fresh because you are drinking like the pH 2. Right? You have a chemical cleaning inside your body, then wash out, especially when you enjoy barbecue, a lot of oil food and fried fish. Again, you drink Coca-Cola because acidic, wash out all your oily condition, so you have a better feeling of your body. But because pH is low, so it damages your teeth. If you stay longer, your Coca-Cola inside your mouth, yeah, the pH dissolves your calcium in your teeth. So slowly release the calcium compound. So you have to rinse your mouth after drink the Coca-Cola. That's a small compound. So only remove the calcium from your teeth. So you have to rinse carefully. And pH 8 is high. If pH 8 is high, which means OH minus is high compared to H plus. The OH minus will affect a lot of precipitation, like calcium hydroxide, magnesium hydroxide, easily combined with your seawater, even iron hydroxide. Make scaling. So you have a scaling body or even membrane, pipeline, pumping, everything you create the more scaling issue. So we have to reduce the pH 8.1 or 2 to 7 or 6. 6 is better because you have less scaling potential. So you have like a stone kidney. Stone kidney, what's the problem? What's the issue? You don't have enough water. You have very high concentration of hydrogen, magnesium, carbonate. So your body creates the salt, hidden salt. When you filter out your hydrogen, magnesium, you have a storage that keep accumulating for your kidney. So same as here, seawater desalination. Seawater contains calcium, magnesium, iron, silica, so many different divalent iron, multivalent iron, which will combine with your OH and create the scaling. So that we need to reduce the pH. And chlorination. So why we chlorinate is seawater. So seawater contains a lot of bacteria, microorganisms. So this will create biofouling, biofilm inside pipeline, inside filters, inside your membrane. Yeah. So they like to remove all the bacteria in seawater. So put the chlorine at the beginning and lower the pH and iron chloride. Iron chloride is a flocculation. So when you have a very high turbidity water, so you want to reduce this kind of turbidity water using the iron flocculation, then settling down. After that, we have a dual media filter. So dual media filter just filter out with sand or anthracite or some of our particles can be removed from the media filter system. And after that, what's the next step is anti-scalant. Yeah. As I mentioned, we will extract water molecule. So your salt concentration will increase to double. Yeah. So we designed for 40% recovery or 50% recovery of your seawater. So you have a very high concentration of salt. This will impact overall your inorganic scaling. So we put some of the anti-scalant to reduce the overall inorganic scaling potential. I will talk about detail later on, what kind of anti-scalant we can put. And dechlorination. So we put the chlorination in front of filter here. And then we are dechlorinating here again. Because reverse osmosis membrane is the polymer. Yeah. So chlorine is the oxidant. So oxidant meets the polymer. It slowly damages the polymer layer, right? It's like the degrading. Yeah. So your polymer active layer in the membrane slowly removed because of oxidation process. The chlorination at the beginning we input because of biofouling, biofilm issues. And then before reverse osmosis membrane, you have to dechlorinate it. That's exactly what we will discuss. So we have to protect our polymer membrane, reverse osmosis. And we will talk about how we can do that. Yeah. And reverse osmosis, next step, reverse osmosis. This is a reverse osmosis. Yeah. This will produce the drinking water from the water. Yeah. How we can design this way, or how many we need this one, and how we can design better way of reverse osmosis. And go for the post treatment with lime. What's the lime?
Yes, you.
CaCO3, right? COH2. So calcium. Lime is a buffer solution. So what happened is that the seawater reverse osmosis remove all the salt, right? So what happens if you drink the pure water? Or if you carry your pure water, yeah, what will happen for your pipeline? So you will damage your pipeline. Even we don't drink the pure water. Yeah? We always drink the mineralized water or buffered water. So what's inside the water is calcium, magnesium. So calcium, magnesium help to reduce your corrosion impact, your stainless pipeline in your pumping system. But if your water is too clean to carry, you will be easily damaged in your overall system. So we need to put the lime, calcium hydroxide, calcium carbonate. This calcium can protect our overall system. And product water, fluoride, and chlorination again. And we can finalize our design. So that's similar to your assignment one. What's the process design from our concept, right? So you can utilize in your assignment first question to design the processes. So you can use the idea, or you can change this one to ultrafiltration. So from the media filter there, the media filter, so you can change the ultrafiltration and you can design it. So it's up to you. After this class today and tomorrow, you can decide ultrafiltration is better or your media filter is more comfortable for the device. So that's how we have to design as the first question. Any other question from this design of processes? So let's look at the more detail, little bit of chemistry. So as I mentioned, this is the pH impact. So seawater pH is A, right? We mentioned about that. So pH A. So we have a more concentration of bicarbonate, HCO3 minus. But when you have a pH 6, we have more CO2, right? And then when you have a more pH higher, pH 10, you have a CO3 2 minus, right? So what's the difference? CO2, HCO3 minus, and CO3 2 minus. What's the difference? So why this is important? in your seawater, your design of seawater desalination plant? So CO2, everybody knows very familiar with CO2. So we are in a problem of CO2 for climate change, right? Yeah. So when you see CO2 concentration is keep increasing, everybody wants to reduce it to protect our climate change. So pH and CO2 has a good relationship together, right? Why? So CO2 increase. So you can see what's the pH impact. So you have a higher pH and CO2 will decrease. How about pH will decrease, right? So let's think about we have an increasing pH CO2 in the air, and this CO2 will decrease the pH in seawater. So in this case, HCO3 minus, which means bicarbonate concentration decrease. So why the bicarbonate is important in seawater? Because we have a pH 8 in seawater for last 1,000, 2,000, 3,000 million years ago. Why pH maintained around 8 in seawater? Because bicarbonate is useful for your ecosystem, like coral, reefs, and crabs, lobsters. So this calcium and combined with the bicarbonate, HCO3 minus, and you can create your shells, your crab's skin, your lobster skin, even coral reef, everything is combined with calcium carbonate. So if you have an increase in CO2, your pH decrease, and then your bicarbonate concentration decrease. So you cannot create any more shells, any more lobster, any more crabs, any more calcium carbonate. So your seawater ecosystem will be very much damaged. So that's why we have a very important relationship between CO2 dissolved in the water and the pH decrease, and then this impact overall our ecosystem of living material in seawater. So that the seawater is pH 8, we have to make less concentration of bicarbonate, which will create the inorganic scaling impact. Also pre-treatment. So when you decide pre-treatment, dual media filtration, conventional process, and ultrafiltration, when you decide which one is better, ultrafiltration would be better, even though capital cost is a little bit expensive. O&M cost is a little bit expensive. Energy cost is similar. Chemical cost is a little bit lesser. And then operation cost, because membrane can design for automatic system. So you can have a better design of membrane. And total cost, ultrafiltration is a little bit higher, little bit. But when you think about quality, so when you have a standard filtration, dual media filtration, your membrane pore size is much smaller here. So your permeate to the reverse osmosis is better quality. So you can protect your reverse osmosis better than your media filter. So it's up to you. What do you want to design? Would be Then filtration or ultrafiltration, which one do you prefer? Ultra. How about you? Ultra. So you have to reflect in your assignment. Design for ultrafiltration rather than pure media. So you can decide why you like to do it. Maybe because of you want to have a positive impact, or you want to have a better positive impact. So that's a trade-off of ultrafiltration, heat treatment, or pure media filtration. So based on that, you will have a different design parameter you can utilize. So that's the how we can think about the pretreatment. And this is the anti-scalant. So how this anti-scalant work? Anti-scalant are surface active material that interfere with the precipitation reaction in three primary ways: threshold, inhibition, crystal modification, and dispersion. What kind of anti-scalant we can utilize? SHMP or NaPO3 6. So why this is important? So you think about this is membrane, yeah. So you have membrane here. So you keep extracting water molecule, and you have a high concentration to accumulate calcium, magnesium in seawater. So because of a high concentration of calcium, magnesium, they combine with the calcium carbonate, calcium sulfate, calcium hydroxide. So they're creating the inorganic scaling. So once you have inorganic scaling, this is a crystal. It's very difficult to remove it. So you clogging all the pores. So your flux is reduced very significantly. So how we can let them avoid the precipitation of your inorganic scaling? Put the SHMP or sodium hexamer phosphate material, which will calcium will combine with the phosphate, and then they are not accumulating on the surface, and then carry to your bird water. Even they are not let them keep growing the crystal, yeah, and this crystal can be avoided from this anti-scalant. So we have to put the anti-scalant. If you want to increase the overall water recovery, well, making sure that you protect your membrane surface without any inorganic scaling issue. So we can put the anti-scalant from your process. So you can decide how much anti-scalant you can add, also how much water recovery, because you extract more and you have a higher concentration of calcium. Other compound will create this kind of scaling. So this is calcium carbonate. So it's covered on the membrane surface. Calcium carbonate, also calcium sulfate. Also they keep growing on the membrane surface. And this is magnesium carbonate. So they are easily covered our membrane, and then we can make sure that the anti-scalant can remove this kind of crystal growth. So we decide what kind of anti-scalant you can do that. So, but not many people have an idea how much concentration we have to add. It depends on the water solubility. But many of you don't have a water chemistry background, right? so that we utilize the wave software. The wave software will predict, depending on your water solubility, how much concentration, how much carbonate you will start to create your inorganic scaling, calcium carbonate, sulfate, magnesium carbonate. So you need to put the anti-scalant if you want to increase your water recovery up to 50%, 60%, your concentration has a very high potential to create this kind of inorganic scaling. So this is all related to water solubility. Yeah. And so how we can decide? You rely on your
The dosing of this anti-scalant is just like chlorine dosing, you just mix it.
the chlorine dosing is not anti-scalant.
Yeah, but the way we do it is how we introduce this anti-scalant is how after filtered water. We just
Okay, before reverse osmosis, because we expect only water molecule. So you have a high source concentration. So this will create the scaling on the membrane surface. So to avoid the membrane scaling, so we put the anti-scalant.
how we dose it.
How? So just liquid, like you put the sodium phosphate hexamers compound in the liquid, you just high concentrated, you put together, you mix together in the seawater and goes to that. Yeah. So next one is dechlorination. So people want to know after you chlorinate it, and you have to dechlorinate it because you damage your polymer membrane oxidation, right? What to do? So this is dechlorination. So we want to remove the chlorine from SBS, the sodium metabisulfite. The sodium metabisulfite combined with the chlorine, and then produce this sodium sulfate, and then finally this chlorine is the oxidant, and converted to the HCl. So it's no more oxidation potential. So it's relatively safe rather than oxidize the polymer membrane, right? So you can just easily put the SPS or granular activated carbon chlorine to chloride ion can be made. So you can remove your chlorine from your pretreatment process. And limes. So lime mineralized water have a few adverse impacts. Also, corrosion potential, dietary deficiency, causing risks of heart and some of the disease. And somebody needs to recommend 10 milligrams per liter of magnesium. So if you drink the 10 milligram mineralized water, this is the good health impact. Also, calcium, 30 milligrams per liter would be best for use to drink. So we like to put after you desalinate most of mineral gone. So we want to add more mineral, magnesium, calcium to have a better mineralized water. The solution widely used to mineralize CO2. So we just inject the CO2 and calcite limestone, calcium carbonate, magnesium, plus sodium carbonate, put into the desalinated water and remineralize. And this is good for our health, good for our buffer solution, good for our protector of the pipeline and pumping. So that's how we design for remineralization. After that, we supply to water, and this will give a better quality of desalinated water. So this is the design of overall. So you can think about how you want to change a little bit from your design assignment. So it's up to you, but this is typically we think about also energy cost 51%. So what's the energy cost of 1 kilowatt hour now? So we pay around $0.3 for 1 kilowatt hour. Yeah,
I pay 27. I pay 27 cents.
we pay 37.
Cent on farming. I pay 27 cents farming.
Okay. 37 cents per unit, right?
But the
Okay,
supply
that's it, $0.3. $0.3.
yeah.
$0.3.
But the supply charge is almost 80 cents.
Okay. So my question is, you pay 1 kilowatt hour energy $0.3, right? So how much is energy required to seawater desalination water? Overall, how much energy do you need to produce the desalination water from this process? Megawatt hours. 1 cubic meter production. 1 cubic meter of water. So you need a 4 kilowatt hour for 1 cubic meter of seawater desalination. So as I mentioned, you pay $0.3 for 1 kilowatt hour. So when you have 1 cubic meter of production of desalinated water, you need 4 kilowatt hours. So which means 1.2 dollars you have to pay to drink 1 cubic meter of desalinated water, right? So that the energy is the highest boiler cost, more than 50%. So you produce a lot of energy. So as I mentioned, 250 million liters per day. How much energy you need per day? Consider desalination. Every day, you have to spend 250,000 multiplied by $1.2. How much for desalination plant every day? $3 million. Are you sure? You need to pay for energy cost every day, every day. 250,000 multiplied by 1.2. 1.2. Huh? $300,000. So city desalination plant, when you produce 250 million liters per day, so you need energy equivalent, and you have to pay $300,000 per day to produce the city desalination plant. Only energy cost. Only energy. This is 50%. The other 50%, monitoring and labor, waste stream, chemical, maintenance, another 50%, which means the everyday desalination plant operating cost more than $500,000 to produce that your desalination water. It's expensive, right? So that's why the people don't like oil. It's too expensive to maintain every day. We spend a lot of energy, a lot of that's the how we have to look at carefully, so that the city desalination plant powered by wind, the renewable energy, not the coal or gas, even any of so it's coming from the wind farm. produce the energy and then try to offset the energy impact from the desalination plant. So we have now we can have a half an hour break. Yeah. And we can start 45, 11. And then we can have a lunch. Yeah. Any questions so far? Otherwise, we can start from our terminology from the next step.
It's
That we have to discuss. Just wait a minute. That's I want to talk about that.
6 years in water.
That's why.
That's convincing water treatment plant have very less cost of treatment.
So if you are wondering what it looks like, these are please enjoy the sample here.
This is ultra treatment. This is membrane.
Yeah.